Hello, my name is Jesse Flores, and I decided to do my project over permanent magnet direct current motor, or a PMDC. What is a DC motor? A DC motor is a direct current motor, or commonly known as the DC motor. It is a type of motor that converts electrical power into mechanical power. A DC motor is one of the simplest types of motors and are used in everyday life. There are four main types of DC motors: the shunt wound motor, the series wound motor, the compound wound motor, and the permanent magnet motor. For my DC motor, I chose the permanent magnet motor. But there are some advantages to this motor. One is it reduces the size and weight of the DC motor. It has a quieter operation and is one of the cheapest forms of a DC motor. But there are also some disadvantages. The magnetic field of this type of DC motor is present at all times, even when the motor is not being used. Mostly used for smaller devices, so they can't take as much strain as the other three DC motors can. Where can you find a permanent magnet direct current motor? These motors are typically found in electric toys such as the electric car pictured, and also computers, refrigerators, and vacuum cleaners use these types of motors. Some assumptions had to be made to be able to model this permanent magnet direct current motor. These assumptions include a rigid rotor and shaft, a single input from a voltage source, a single output as an angular velocity, rotor inertia J equal to 0.02, viscous dampening coefficient B is equal to 0.25, K equal to 0.03, resistance R equal to 0.9 ohms, and inductance is L equal to 0.05. All of these values are just made up values to be able to model this permanent magnet direct current motor. The equation used to model this permanent magnet direct current motor is K over J times S plus B times L times S plus R plus K to the second. This formula came from a block diagram of a DC motor. The assumed values were plotted in MATLAB, and with a step response, we found a settling time of 0.331 and a final value of 0.117. And with these values, I'm using the root locus or the CISO tool, you can manipulate some of these values to be able to get some other parameters that you feel more comfortable with, or just mess around and see what other values you can get. After finding your step response, I decided to set some response goals, and some of the goals are a settling time of less than 0.1 seconds, a rise time of less than 0.3 seconds, a percent overshoot of less than 6%, and a final value of 1. These will be plotted in the root locus with the CISO tool. In my final results, after plotting my results in MATLAB, I ended up with a rise time of 0.00119, a settling time of 0.0075, and a final value of 1. All of these values meet or beat my goals of rise time, settling time, and final value and percent overshoot. In conclusion, my goals were achieved with a settling time of under 0.1 seconds, a rise time under 0.3 seconds, and a final value of 1. Utilizing the CISO tool helps save time and money because of how easy it is to be manipulated by different types of controls. Example, the PI and the PID controllers. Thank you.